All right, the second lecture in Unit 3 is on energy. So, how are people, machines, and Earth able to do mechanical work? So, the answer is energy. Energy is the ability to do work. So, energy comes in many different forms. But energy is a scalar quantity. There's not a direction associated with it. It is measured in joules, just like we measure work. So here's some notes to copy down about energy. It's the ability to do work, comes in many forms, it's scalar, and it's measured in joules, just as I said earlier. So there's different types of energy. One of the mechanical types of energy is kinetic energy. And kinetic energy is the energy that's possessed by moving objects. So we could say that if you have a hammer and you wanted to push a nail into a piece of wood, the work done is the force times the displacement. The energy that the hammer has, it would increase if we have a more massive hammerhead, and it would increase if the hammer's moving faster. So if you just have a hammer and just lightly tap on a nail, it won't move into a board as much as if you're swinging the hammer to hit the nail. So in general, the kinetic energy of an object of mass m traveling at speed v is given by this equation. So the kinetic energy is measured as 1/2 mass times velocity squared. So just as I said, the faster the hammer moves, the greater its mass, the greater its kinetic energy, and the greater the displacement of the nail. So the more work that it does. So here's one of our first equations for this unit. EK equals 1/2 mv squared. And here's a question to do. This one's a simple calculation. What is the energy done by a 480 gram lawn dart traveling at 3.4 meters per second? So it is 0.5 times its mass, which is 0.48, times its speed, 3.4, squared. And we get 2.77. We have two significant digits in the 480 grams. We have 2 in the 3.4 meters per second. So our kinetic energy has to be represented with 2 significant digits, which is 2.8 in this case. Softball with a mass of 170 grams has a kinetic energy of 98 joules. What is its velocity? Let's work this one out on paper, because we're going to rearrange the equation. So if we have this softball, we know that the kinetic energy is equal to 0.5 mv squared. We need to find the velocity. So to move this 0.5 to the other side of the equation, it's the same as dividing by 0.5 or multiplying by 2. So let's multiply by 2. So we have 2 EK equals mv squared. We need to get the v squared by itself. So we divide the other side by m. And I just moved them around so that I have my v on the left side. And then we have to find the square root. So the square root of 2 EK over m. That's what our v would be equal to. We're going to do our substitutions. The energy is 98. The mass is 0.17. And now we can calculate this. So 2 times 98 divided by 0.17. We have this value underneath our square root. So now let's square root that. I'll raise it to the power of 0.5, which is equivalent to a square root. And we get 33.95, which because we have two significant digits, would round to 34 meters per second. So we've talked about kinetic energy. Another type of mechanical energy is potential energy. So this is the energy that is stored in an object. So when do we have potential energy? Well, if you have, say, a bowling ball resting on the floor, the bowling ball cannot fall any further. So it doesn't have potential energy when it's on the floor. But if there's a bowling ball and it's on top of a cabinet, for example, the bowling ball has potential energy because it could potentially fall off that cabinet and do some work by maybe damaging the floor, causing a displacement on the floor. So that is potential energy. And I guess specifically that's gravitational potential energy, which is one of the most common types of potential energy we talk about. You could also have potential energy in food, for example. When you eat, if you look at the nutritional notes on or the nutritional facts or information on any type of food product that's sold in Canada, you'll see that it lists how much energy something has in joules. Well, in order to get that energy, that's the potential energy inside the food. In order to get that energy, your body has to process it. And through the processing of that, you can then use that energy. So that's a chemical potential energy that's in our food. But the one type of potential energy we're going to talk about mostly in physics is gravitational potential energy. So it's more of the bowling ball example than the food example. An object that is raised to a position above the floor has the ability to fall and gain kinetic energy. So through its gain of kinetic energy, it could then do work. So we call the energy gained by an object through raising it against a gravitational field the gravitational potential energy. And it is equal to the mass of the object times the gravitational intensity on the planet, I suppose, times the height that the object is raised. So on Earth, G is going to be it will be 9.8 newtons per kilogram. But your mass of your object and your height have to also be considered. Here we have a construction worker with a sledgehammer. A sledgehammer has a lot of mass compared to other types of hammers to allow for more work to be done when it is struck. The higher the sledgehammer is raised, the more gravitational potential energy it has because it can gain more kinetic energy as it starts to fall down. So here is a slide to copy down for gravitational potential energy. It's the energy possessed by an object due to its position relative to Earth. Eg, the subscript is G for gravitational potential energy, and it's equal to mgh. The G is measured in newtons per kilogram, but it is equivalent to the acceleration due to gravity on Earth. So it could also be considered as meters per second squared. So here's a situation where we have a flight of stairs with different levels of height. It says a 58 kilogram person walks down a flight of stairs. Let's use ground as our reference level. It says calculate the person's gravitational potential energy at the top of the stairs, on the landing, and at ground level. So these are relatively easy calculations to do. I'll pull them up on our calculator here. 58 times 9.8 times the height at the top of the stairs, which is 6. Sorry, that's not right. 58 times 9.8 times 6 gets us to 3,400 when we round for significant digits. 58 times 9.8 times 3 at the landing is 1,700. And I'll do this on the calculator just for completion purposes. 58 times 9.8 times the ground floor, which is 0, gets us 0 for our work gravitational potential energy at the bottom level of the stairs. So what happens to the gravitational potential energy as you walk up or down a set of stairs? So as our height increases, our gravitational potential energy increases. And the opposite is true. As the height decreases, the gravitational potential energy decreases. So there are animals that actually use the idea of gravitational potential energy. One of them is the vulture. So the bearded vulture, it can't break into bones of carrion that it finds using its beak. But what it can do is pick up those bones and fly very high and then drop those bones on rocks. And depending on how much gravitational potential energy the bones gain as they are raised, they could potentially break on the rocks. So these vultures do this. They try to drop the rocks on top of, drop the bones on top of rocks. Once the bones break, then they can start to eat the bone marrow that's inside of those bones. So that is how a vulture uses gravitational potential energy. So I talked about mechanical energy, but I haven't really defined it yet. So objects don't have either potential energy or kinetic energy. They could, but they could also have a combination of those. So here's some situations. Let's say we have a hockey puck that's sliding on ice. Well, it would have kinetic energy only because it's already at the ground level. An acorn hanging in a tree has gravitational potential energy because it's not moving. But a parachutist who's falling, they have both gravitational potential energy and kinetic energy because they're both moving and they are above the reference position of the ground on Earth. So mechanical energy is actually a combination of your kinetic energy plus the gravitational potential energy. That's how we define mechanical energy. So, if the speed or the height of an object changes, that means that work was done. In other words, work is a change in energy. So this relationship between energy and mechanical work is known as the work-energy principle. So the idea here is that if work is done, if something starts to move, and we know the energy that was available through something's kinetic energy or its potential energy, gravitational potential energy, or I guess you can just say it's mechanical energy, then the change in that mechanical energy is equal to the work that is done. That's the work-energy principle. And it's written there algebraically. The net work done is equal to the change in mechanical energy. So you can also find it as the mechanical energy final is minus the mechanical energy initial is equal to the work. And we'll do this. I think this is our last question. It says a 13 kilogram object traveling at 10 meters per second accelerates to a speed of 14 meters per second over a displacement of 8.2 meters. Calculate the net work done on the car. And it says, hint, if you find the force using acceleration, then use work equals force times distance. But there's an easier way. So think of the change in energy. So that hint is important because you could answer this kinematically using what we learned in Unit 1. But we could answer this a bit of an easier way. So the kinematic solution would look at this question and say we have 10 meters per second is our VI, 14 meters per second is our VF. We have our displacement, so we can find our acceleration, and then we can use what we learned in Unit 2, F equals ma, to determine what the force applied is. And then we can take our force and multiply it by our displacement of 8.2, and we can solve for the work done. So that was quite a bit of steps. There is a faster way to do this, so I will show you that. If we just think of how our energy changes in this case, so we have for 4A, our work is equal to our EM final minus our EM initial. EM is our mechanical energy, and we know that our mechanical energy in this case, because it's just an object moving at ground level, it is essentially just our change in kinetic energy. So EKF minus EKI. Our work is then it's 1/2 0.5 mvf squared minus 0.5 mvi squared. And just for to make this a little bit simpler, I'll factor out the 0.5 m. So what we're really doing is 0.5 times m, which is 13, times vf squared, which is 14 squared, minus 10 squared. So let's turn on our calculator. 0.5 times 13 times bracket 14 squared minus 10 squared. Close the bracket, press equals 624. And we have two significant digits in as our minimum amount of significant digits here. So we round to 620. And that is in joules. Now, that is an easier way to solve this, but you could have solved this using your understanding of kinematics, right? So going back, if you were going to use kinematics, you would first find the acceleration using the VI, VF, and the delta D. Then you would use Newton's second law, which is F equals ma, to find the F. So you would take that 13 mass and multiply it by your A. And then you would multiply your displacement times your force. And that would get you your work done. But this is a bit of an easier solution. So we could also do it this way. Now let's look at our next question. Calculate the net force acting on the car. Well, now that we have our work of 624, or 620 as it's rounded, we can find our force. So let's go back to our camera here. So work equals force times distance, or displacement. Force is equal to work over displacement. We need to substitute in the exact value of 624, not our rounded value up here, or our what's called our reported value. The reported value has to be based on the significant digits in our measurements that are given. But when we're doing calculations or intermediary calculations like this, we need to use the actual calculated value of 624. Then we have to divide by our displacement, which is 8.2. So calculator on, 624 divided by 8.2 we have 76, and that would be newtons. That is our force. And again, going through this again, we could have solved for our force by using kinematics to solve for A, and then used Newton's second law, F equals ma, to solve for F. But using what we learn in this unit, the conservation of energy, but the work is equal to the difference in mechanical energy. We can find the work, and then we can use that work and the work equals force times displacement equation to find our force.